Today, we want to grab an older problem with a slight twist on it. I want to find the equation of a line tangent to the circle, x squared plus y squared equals 25 at the point 3, 4. So what is the same about what's going on this problem? I want to find the equation of a line tangent to some curve. What's different is that the curve is described with an equation, not a function. That's the new twist today. So we can see, so here's the old problem. The equation of line tangent. That's an old problem. But this x squared plus y squared equals 25, that's our new twist. The difference is that instead of giving you a function and asking for the equation of the line tangent to some function, we're defining the curve with an equation that's not a function. So the new twist is that the curve is described with an equation rather than a function. That's our new twist. I described the curve with an equation rather than a function. We know that the equation x squared plus y squared equals 25 is going to produce a circle, partially because I said it's a circle and partially because it looks like x squared plus y squared equals r squared. It's a circle with a center at the origin and a radius of 5. When it comes to drawing a circle on a set of coordinates, always draw the circle first, then draw your coordinates underneath it. Then pretend like you drew it the other way around, and you're just that skilled in drawing circles. So this is not a new problem. Find the equation of a line tangent to a curve. Find the equation of a line tangent to a curve at a given point. So here's the point 3, 4. And there's going to be a line tangent to it. The difference is that our curve is described with an equation, not a function. Oh, it's right over here. No, I already wrote that. Curve is described with an equation rather than a function. So we have a couple of things that we could do to approach this problem. One of them is our favorite trick of the 3 great tricks of mathematics. When we add 0, multiply by 1, do a problem that you already know how to do. That's what we're going to do. We're going to take this problem, this new twist on this old problem, and just turn it into an old problem. So step 3, or trick number 3, do an old problem. We're going to look at 2 ways to approach the problem. Number 1 is just do old stuff. Do an old problem. We do have a skill set that says, here's a function, take the derivative, plug in the points for your slope. So we're going to take our equation and turn it into a function. That's how we're going to deal with this. Take our equation and turn it into a function. Because we know how to find the equation of a line tangent to a function at a given point. When the curve is described with a function, we have a tool for that. Take the derivative, plug in the x, find the equation of a line. So we're going to start with our equation, x squared plus y squared equals 25. And we're going to write y as a function of x. We're going to solve for y. So our strategy is to write y as a function of x, that is, solve for y. We're just going to write y, rewrite this where it says y equals. We know we're going to run into an issue with this because this circle cannot be described with just one function. Here is an x that corresponds to two different y's. It fails the vertical line test. Each input has more than one output, or some inputs have more than one output. So we should be on the lookout for that. We know we can't write y, this whole circle, as one function of x. But we see exactly where that's going to happen because y is being squared. We can see why these x's correspond to two different y's. So we say y squared is equal to 25 minus x squared. And now we have to get rid of the square. And this is where our two solutions come up. Y is equal to plus or minus the square root of 25 minus x squared. The issue of writing this equation, solving this equation for y, is that we don't end up with a function. We end up with two functions. This circle is two functions of x. The circle needs two functions of x. Fortunately, we have the point 3, 4, so we know which one we want. There's two functions, y is equal to plus the square root and y is equal to minus the square root. Since the y value is 4, clearly we want the one where y is positive square root. We want f of x to be the positive square root of 25 minus x squared, because we're looking at a point on the top half of the circle where y is positive. The point that we're given has a positive value of y, so we want where y is positive. We want the top semicircle where y is positive. The plus or minus describe the top semicircle and the bottom semicircle. Y equals plus square root of 25 minus x squared is the top semicircle. Y equals minus square root of 25 minus x squared is the bottom semicircle. We can also solve the equation for x, where we'll still have a plus or minus 25 minus y squared in this case. That would just be the right and the left semicircle. We're going to solve for y because we're going to find the equation of a line. And the way we define direction on a line is the slope, and the slope is the change in y divided by the change in x. If I use the x one, it would be upside down. I'd end up with change in x divided by change in y, and our equation would have to be written differently. So I've got my equation for the top half of the semicircle. I don't care what's going on in the bottom half. F of x is square root of 25 minus x squared. We're super experts at taking derivatives, although I spelled 2 wrong. We're going to read f as this 25 minus x squared to the 1/2 power. So our derivative will be 1/2 25 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Our derivative is purely a function of x, so I'm just going to grab the x coordinate of the point we're interested in. We're interested in what's going on when x is equal to 3. So I want to find f prime of 3. We're interested in what's going on at x equals 3. I dropped something somewhere. Forgot that negative. So we get a slope of negative 3/4. That's going to be our slope. Just like we always do. Take the derivative, plug in the point, that's your slope. We have the point is 3/4. So we can write the equation of the line. Y equals 4 minus 3/4 times x minus 3. There's a line containing the point 3/4 with a slope of negative 3/4. We were able to do this problem using our old technique. Even though we can't write a function for an entire circle, we only need to know what's going on in that top half of the circle. And if I change the point that we're interested in, if I change to a different point, like the point 4, negative 3, we just have to be aware that the slope is going to be coming from the bottom half of the circle. So if we change things up a little bit, we can still do the problem. If I have the point 4, negative 3, then I'm going to want the bottom semicircle. What we want to notice here is that we just have to be aware that when we solve for y, because y was being squared, when we solve for y, we've introduced a plus or a minus square root. We can't just square root things. There's a plus or minus. And we want to know that that geometrically corresponds to the top half, the top semicircle, and the bottom semicircle. So in this case, where we see on the previous problem that negative slope on the bottom semicircle, we know we'll have a positive slope. And here's where we're going to see that negative cancel out, the negative that I almost dropped from the first one. So we get a very similar thing, a similar derivative, but it's positive x. So that when we plug in our new x value, we'll have a positive slope. So I've changed things up to plug in a 4, x equals 4. So we have a slope of positive 4/3. One way we can solve this problem, if solving the problem was the point, if just find the equation of a tangent line was the point, we have a way to do that. There's a little bit extra. We have to recognize that the circle cannot be represented with one function, because a function requires that each input correspond to exactly one output, or at most one output. And here we have some inputs, some x's that correspond to two different y's. Is everybody okay? I think it's very serious. Oh, tangent lines. This is that original problem, so it must be important. I can tell that when I'm working on the mission to Mars for Mars Corp, I'll be happy to find equations of tangent lines. If finding the equation was the point of the problem, then we would be done. But it was clearly not, because I labeled this as one way to do the problem. And I clearly said that there will be two ways to approach the problem. Number 2 is the new thing for today. So the new thing for today is implicit differentiation. When the problem says find the equation of a line, one of the things that we need to find is the slope. The slope is just change in y divided by change in x. We're finding the slope of a line tangent to a curve, so we're going to use a derivative. dy over dx. We need the slope, so we need dy over dx. We're going to go about getting that in a slightly different way. We need to find slope. You need to find a slope, which is delta y over delta x, but it's a tangent line. So our slope is going to be dy over dx. Our x's and y's are going to be all mixed up. What we're going to use here is the chain rule. What we're going to do is take the derivative with respect to y and then multiply by the derivative of y with respect to x. To find dy dx, we take the derivative with respect to y and multiply by the derivative of y with respect to x. This is how the chain rule operates, and this is how we're going to install a dy over dx. The derivative with respect to y times the derivative of y with respect to x. Implicit differentiation is a technique that we're going to use when the x and y are related to each other in some fashion. So this is not a function of two variables where the x and y are independent. Implicit differentiation is how we're going to find dy dx when y and x are related but not by a function. When you say stuff like in math, in words, it just comes out forever because it's like, oh, but this, and then when it's this, then. But since it's a Tuesday, then that does not count as a Fizbin. If this had been a Wednesday, then that would have been a royal Fizbin. But no one's seen that episode of Star Trek, so. I also make reference to the movie The Matrix, and that movie is like older than all of you, so there's that. So why not go with a reference that was 5 years old at the time that I was born? Now I just need to go find a reference that was 5 years old when William Shatner was born. That's when you find out William Shatner was like 92 years old. He's like still like working. But does he answer my call to come cover a class? No. What does he do instead? Gets a restraining order. I'm just kidding. He doesn't have a restraining order against me. I don't use my real name when I'm stalking celebrities. He has a restraining order against a person that doesn't even exist. I'm just kidding. They found out it was me. I'm just kidding. They haven't found me yet. I'm just kidding. This is all made up. He'll call me. But anyway, at the office though, I mean, let's be reasonable. And I was like, oh, it'd be really cool if you could like beam into class. And he's like, oh, you realize that was made up for the show and I can't actually do that. I'm like, yeah, but it would be really cool if I could just be like, oh, I have a guest speaker. I pick up my phone and I go, energize. William Shatner is here and he does the lecture. So implicit differentiation. This is what we're going to do to find dy dx when y is not a function of x. That's the point of this implicit differentiation business. Find dy dx This is for when y and x are related, but not when y is a function of x or x is a function of y. This is an important distinction to make because later on you'll be having functions of two variables and the x and y won't be related. So this is when y and x are related. So here's what we're going to do. We're going to go through and we're just going to take this equation. That's our relationship between y and x. It's an equation, not a function. The important thing is not a function. And I'm just going to go through and I'm going to take the derivative with respect to x all the way through. So I'm just going to take the derivative with respect to x. If you don't like this, you could say I'm taking the derivative with respect to x on both sides. But this way, I only have to write d over dx one time, and I don't have to try to jam one in there between the equal sign and the 25. I'm just going to go a term at a time because that's how derivatives work. Differentiation is a linear transformation. So the derivative with respect to x of x squared is 2x. The next term is y squared. That's a function of y. I am going to write 2y, but that's the derivative with respect to y. So when I write 2y, that's the derivative with respect to y. Because I used y as the variable. I said y squared, the derivative is 2y. That's a derivative with respect to y. When I say with respect to y, that means I was treating y as the variable. Then the chain rule says if you want the derivative with respect to x, you take the derivative with respect to y and multiply by the derivative of y with respect to x. We don't know what that is, but that's what we're looking for. So we just apply the chain rule, and what we're looking for shows up. On the other side, the derivative of 25 is 0 because 25 is constants. So the times dy dx, that's the chain rule. The x squared derivative and the 25 derivative, those are just like normal. But when we write 2y, that's the derivative with respect to y. The chain rule says multiply by the derivative of y with respect to x. But we took y as our inside function. Now, if it's convenient, we can solve for dy dx, which it is in this case. So dy dx. I'll subtract 2x from both sides and divide by 2y. So 2x divided by negative 2y. So subtract 2x from both sides, divide by 2y. So if I want the slope of the line at the point 3, 4, it'd be negative 3/4. That's the slope that we had on the previous page. If I want the slope at the point 4, negative 3, there's that positive 4/3 slope that we had on the previous page. In Leibniz notation, if you want to show that you've plugged in a point, since it doesn't come with a set of parentheses where you put the input, you just write a vertical line. That's a common math notation for take this expression and evaluate it for these values. So just a vertical line says evaluated at these points. That's everybody okay? So this is consistent with these points because these are the same two slopes we had on the previous page. Furthermore, remember what we did on the previous page was solve for y. Y is equal to plus or minus the square root of 25 minus x squared. And look where the y is down here. If I replace the y down here with plus or minus the square root of 25 minus x squared, I get the two different expressions that we had before. In the top half of the circle, I replace it with the plus square root of 25 minus x squared. And in the bottom semicircle, I replace it with a minus, and that causes things to cancel out. So still consistent. If I want the top semicircle, then y is plus square root, and I get negative x over the square root of 25 minus x squared. If I want the bottom semicircle, then y is negative square root, and I get the negatives cancel out, and I get x over the square root of 25 minus x squared. Any questions? Is everybody okay? Everybody looks so stoked. You all look like this. And I'm just going to go ahead and assume that that's your stoked face because we just learned about implicit differentiation, which is super cool. At this point, it's just a matter of getting used to finding dy dx through implicit differentiation. So if we had some weirdo function, if I had, let's say, 2x cubed y to the 4th equals 10. Let's put something else over here. Let's say this is 10x minus 3, minus 7. Something we haven't used before. This is clearly a very important function and not just some random function that I made up on the spot right now. This will come up later. But only if I remember to randomly generate this function again. About training. Some days you just got to do lateral raises. So what we're going to do is take the derivative with respect to x of each of the terms. Now, what we've got to remember is that x and y are related. We've got to remember that x and y are related. So this, here we can't really solve for y. We'd have a plus or minus 4th root. And there'd be 4 of them. 2 of them would be complex. We don't have to worry about them. But they're going to be like plus or minus 4th root. So we could go that way, or we could use our fancy implicit differentiation to take the derivative with respect to x of this whole thing. The thing that we have to remember is that here is some x in this x to the third. This y to the fourth has a bunch of x stuff in it. So I've got some x in this x cubed, and I've got some more x hidden in this y to the fourth. So I got to treat this with the product rule. There's some x here. There's some more x hidden in this y. So we're going to use the product rule. So we're going to have to use the product rule. Our first function is the 2x cubed, and our second function is going to be a y to the fourth. That's what we're going to have in our product rule. Our f we can write as 2x to the third, and our g can be y to the fourth. So our f prime, the derivative of the first, will be 6x squared, and our g prime will be 4y to the third. That's the derivative with respect to y. So the chain rule says multiply by the derivative of y with respect to x. I was treating y as the variable, so I have to multiply by the derivative of y with respect to x. So for this, I need the derivative of the first times the second plus the first times the derivative of the second. That's just on this left side. Then on the other side, the derivative of 10x with respect to x is 10. And the derivative of 7 with respect to x is 0. When we're reading an equation with implicit differentiation, we're looking at a relationship between x and y. That's the time to use implicit differentiation. You have to treat treat the y as having a bunch of x in it. And so in this case, that required us to use the product rule along with the chain rule. Now, in this equation, we could solve for dy dx. I need to subtract the 6x squared y to the fourth. I'm going to clean this up. This is going to be 8x cubed y cubed times dy dx. I'll subtract 6x squared y to the fourth, and I can just divide by the coefficients. Oh, we could drop a 2 out of all this. So this is implicit differentiation. This is just knowing that the y and the x are related by this equation and avoiding the complication of solving for y, trying to write y as a function of x, either because we can't or it would just be messy. In this case, it wouldn't be so bad because y only appears one time. In this one, we actually could write y as 2 different functions of x, but if I put a y at the end of the 7, like I originally intended, all of a sudden we can't solve for y anymore. And we have to do this. Any questions? Is everybody okay? You want to see that we're using the chain rule. We were looking for dy dx. That's the slope of the line tangent to a function. How y is changing when x increases by 1. When we look at the factor y to the fourth and think 4y to the third, that's the derivative with respect to y. We want the derivative of y with respect to x, we multiply by dy dx. That's how the dy dx shows up. Got to write y on the 7. So as soon as I started taking the derivative, I'm like, oh, wait, we're not supposed to be able to solve for y, but the one that I wrote, we can solve for y. It's just a little bit messy. You have to be conscious of what we are doing. We just need some situational awareness. All right, so that's the idea behind implicit differentiation. It's finding derivatives, it's finding dy dx, it's doing the same stuff. We just have to think, we see that y and think that is related to x, so we think of that as having some hidden x in it. That's it for today. I will see you all on tomorrow. We'll do some more implicit differentiation. Everybody have a good day. Thanks for playing.